Exercise 2225 wants you to draw a mechanism. And when you look at the reaction, at first it might look a little strange. You see that you're forming a ring. You have a straight chain and you're creating a ring out of it. But one feature that should be very evocative for you is that you have this ketone, and next to the ketone you have an alpha-beta unsaturation. And that is a sign of a that is the sign of an aldol condensation. An aldol condensation. And when you look, you see that we have the recipe for an aldol condensation here. NaOH and heat, and there should also be some water there. So it may not be written on your sheets, but there should be water in this mixture. You'll see that we'll use water in the mechanism. Okay, so how does that form? Well, you might remember that so what we know we're doing is an aldol condensation. There are two parts. The first part is really just the aldol addition. And then the second part will be the elimination, or the condensation. So let's take our original molecule. When we treat this with a base, the base is going to steal an alpha hydrogen. Now you'll notice this molecule has some symmetry down the center. And so really there are two places where you could have alpha hydrogens that are acidic. One is on the end and one is in the middle. They're asking us for what creates this ring, this five-membered ring. We know that wherever the hydrogen gets ripped off, that will get turned into a nucleophile. And so that would attack this carbonyl carbon here. Now if the hydrogen gets ripped off on the left, let me draw that in so you could see that. Let's say the sodium hydroxide swoops in and steals the hydrogen on the left. The electrons snap back onto the carbon there. And what you end up with is this nucleophile here. Excuse me. That nucleophile there, let me put that in red so we can make more visual connections. You see the slight blue, positive charge of that carbonyl here. It's going to be really hard for this carbon to attack that carbonyl carbon and make a ring, because you would have a lot of ring strain. There would only be 3 atoms in the ring. That would be like a triangle, and the angles would be 60 degrees. But this is an sp3 hybridized carbon, and so is this one, so they would prefer to be 109.5 degrees. And so that has a lot of ring strain, and so that is not going to be the molecule that creates the ring. Even if it did create the ring, it would create a 3-membered ring, not a 5-membered ring. And so that's not the mechanism that we want here, even if that is something that could theoretically happen. They want us to show how this transformation could happen. So instead of having the base attack that alpha hydrogen, we're going to have it attack the other alpha hydrogen. So it can steal that hydrogen, the electrons that were holding it on would snap back onto that alpha carbon there, and this is a proton transfer. Okay, so after that proton transfer, we have a nucleophile on that carbon. The electrons in that bond turn into a lone pair that can act as a nucleophile. And as we saw, the carbonyl carbon further along in the chain can act as an electrophile. And you'll see this a lot in biochemistry. You'll see how things can form rings when one part of a molecule acts as a nucleophile and a separate part acts as an electrophile. It happens especially when sugars form rings. In any event, this carbon nucleophile can walk around, wiggle around, attack that carbonyl carbon, the pi bond would break, the electrons go onto that oxygen there, and so what you have here is nucleophilic attack. Now, that's going to form a ring. And anytime you go from a ring to a straight chain, or from a straight chain to a ring, I find it's really useful to number the carbons, rather than try to just do mental acrobatics and visualize it. So I'm numbering this as 3, 4, 5, 6. Now notice we're going to have 5 carbons in our ring. So these 5 carbons are going to be part of the ring. Carbon 1 is going to be attached to carbon 5. So let's draw a 5-membered ring, and then we'll number these. So this is carbon number 1, 2, 3, 4, 5. You could have numbered it any way you want. You'll get the same molecule. It may look a little different, but it would be the same molecule. On carbon number 2, we're going to have a carbonyl. On carbon number 5, we're going to have 2 things. We're going to have a single bond to an oxygen, which now has 3 lone pairs and a full negative charge, and we'll also have a methyl group, the 6th carbon. Okay, so that's our product so far. Now, once you have that, you're going to stabilize that negative oxygen by doing a proton transfer from water. This is why it's important to have water in that recipe. So it attacks that. The electrons snap back onto the oxygen, the most electronegative place nearby, and that is a proton transfer that you're doing to change the stability of that oxygen. Okay, so that's the end of the aldol addition. That's part 1. The alpha carbon of one aldehyde or ketone attacks the carbonyl of a second, and you get a beta hydroxy aldehyde or ketone, in this case ketone. So notice carbonyl carbon, alpha carbon. On the beta carbon, you have this hydroxy group. Okay, so that's the first part. The second part is to do an elimination. And to do an elimination, you have to make sure that there's heat in your reaction mixture. Otherwise, you stop here. If there's heat, then you can do this elimination. There's enough energy jostling around to make this happen. So you have your hydroxy group, and that hydroxy group is going to steal the most vulnerable hydrogen, which is the alpha hydrogen still. Notice that we still have an alpha hydrogen there. So the base can steal that hydrogen. The electrons would snap back onto the carbon. Now you have this unstable negative charge on that carbon there. And here's where you do the elimination. This now will exist in equilibrium. It's going to fight for a place on this neighboring carbon next door, the beta carbon. This is going to try to form a pi bond and kick the hydroxy group off. The hydroxy group is going to try to come back on, but both of these two molecules will exist in an equilibrium, sometimes when the carbon wins, sometimes when the hydroxy group wins. If the carbon wins, then you form a pi bond there. And the hydroxy group leaves. And so you end up with your alpha-beta unsaturated ketone. And that was the ketone that they wanted us to explain the creation of up here. So we did the aldol addition, and then we did the elimination reaction. And that gave us our aldol condensation product. And it's interesting to see that done. We've already made a video where we showed the mechanism for this, but but I wanted you to see how it can happen intramolecularly to create a ring. So within just one molecule to create a ring, since it's such a common thing that you'll see in biochemistry. And it's also very useful because remember, rings communicate messages more reliably. They have a more rigid shape. The bonds in rings can't rotate 360 degrees like they can in straight chains. And so there's a more rigid shape, and so that those rings, their shape is more reliable. They will fit more reliably into receptor sites than straight chains can. And so it's always useful to think of how you can form those rings, because that allows you to form more potent chemical messengers.